predict it and plan for it in advance. And then this is now where the system comes in. A level deeper even is where there's systemic structures. So this is where you can design the system, basically, the systemic structures. And that's what has influenced the patterns, what has led, for example, to climate change, what has led to your body being sick or having unhealthy developments. And in the case of climate change, often an argument is economic growth or monocultures, right? So this is the systems level, which determines the patterns, which then leads to the events that you react to usually. And beneath this even, and that's especially in economic or social systems, or even in environmental systems, you have this in ecosystem, right? Ecosystem is another system, a term we probably often use, is what values, assumptions, and beliefs shape the systems. That would be for economic and societal systems. But you could also have in ecosystems, there would be some goals that the system strives towards. So this is then mental models, that certain beliefs we have. If we believe we should act a certain way, if we believe that we need to be fair, or we need to be just, or if we believe we have to earn more and we need to grow more. And these are the things where you can, some would argue, transform a system. Any questions or comments to this framework? Okay, so that's kind of the relation between systems and what we observe. So basically what I try to say here is that even like everything is a system, and there's systemic structure underlying almost everything we can see and that happens. An important point is, and you've probably heard this, all systems are more than the sum of their parts. Who has heard this phrase before? Yeah. Anyone would like to try explaining what it means? Yeah.
Brain is like capable of doing all those tasks. That's probably an example.
Yeah, it's a good one. Yeah, so it just means that so the example given was that a brain is made up of a lot of individual neurons, but just summing up those neurons doesn't tell you what the activity of the brain can achieve. And that is for systems in general. So just by summing up parts of the system doesn't mean you can understand what the behavior of the system is like, because in a system, different elements of the system interact with each other, from which a behavior arises. And that's more than just adding them on one to another. And so what are the elements, basically? Why are systems more than the sum of its parts? Because they interact. And one of the elements that makes them interact and determines system behavior is accumulation. And accumulation is something that we don't tend to think about a lot, although it happens. So for example, accumulation could be very simple, a bathtub, right? So you fill your bathtub, and then over time the water accumulates, and the stock changes, so that the water that accumulates in your bathtub is a stock, basically. That's the level of water, and that's the stock. And this changes through an in and an outflow. And so changes in stocks are caused by in and outflows. That's very important in systems. You will see later why. Second one is there's feedback between elements. So elements don't just independently act and react. They react to each other. Also, again, an example with a bathtub, that's what system dynamicists really like to use, is, for example, you have a shower and you try to get the water temperature right? First you turn it on, it might be a bit too cold, then you feel it's too cold, you turn it on warmer. And then you see, oh, okay, you turn it on warm, it might be too warm, so you adjust until the feedback and you've reached the level you want to reach. So there's feedback between the elements. It's not just me turning on the water and it appearing exactly as I wanted. So there's feedback in the system. It can also be more complicated feedback, as we'll see later. So there is a relationship between the variables in the system, and the components of the system create feedback loops. And the effect of accumulation and feedback actually leads to delays. Filling up the bathtub and emptying it. So once you've filled it up, right, it takes time until it's filled up, as well as emptying it takes time. It's not something that happens in an instant. There's a delay, so time matters in the system because of the effect of accumulation. And accumulation actually also means that a stock can go empty or overflow. If you have a stock, it means you have this principle of emptying the stock or the stock overflowing, which is very important, because if we don't think of something in terms of a stock, we just think it's unlimited if we don't have a limit in it. The stock also provides a limit for in and outflow. So delays affect systems behavior, and actually accumulation, feedback, and delays all together lead to non-linear behavior of a system. What is meant by non-linear? It doesn't mean that there isn't a line anymore. I can still draw a line, but it's not a straight line. So it might be exponential growth, logarithmic behavior, S-shaped curve, all of this. But what it basically doesn't, what it means is that it's not a straight line. It goes from here to here, because there's several feedbacks and delays involved over time, which make the curve look much more screwed up. Let's say it like this. So these are the four elements that are characteristic for systems and system dynamics and behavior over time. And are there any questions to this? The reason why it's important and why system dynamicists like to talk about it is because it's not something we're used to think about. We don't think about accumulation usually. We learn about differential equations in school, and that's basically what to do here. But when you think in your daily life, you don't think about this, and you also don't really often think about the feedback. You think like, oh, what will happen if I do this? Then that happens. But you often don't think back like, okay, so if I don't know, if I decide to go somewhere, it's just like I decide to do this and then this happens, right? But I don't always then think back, so what other consequences could be linked to this? How would that feedback again? And so on and so forth. Yeah. So this is something you've probably seen. And these are the 17 development goals, the Sustainable Development Goals, the SDGs. And actually, each of those goals is a system, right? Represents a system, represents part of a system, and they are all in the system. Anything that strikes you when you look at it here? I mean, it looks very ordered, right? And straightforward. So, yeah, climate action, for example, one of the goals. As I said, each of this is a system, and each of this is a complicated and complex system, because systems in general don't tend to be simple and easy. So taking the example of climate change, which is goal 13, who knows how climate change works or has heard or learned about it? Yeah. Okay. Actually, what you can see here, it's already portrayed a bit system-like, right? It's not just a line, a straight line, but there is like solar radiation coming to the Earth. Then you have the greenhouse gases. Some of them get radiated and reflected, while others get trapped in the atmosphere. So this is already showing that there's a whole system involved in the dynamics of climate change. And Okay, so there is a whole system in the dynamics of climate change, and that generally natural scientists tend to think much more in systems than economists do. So in biology, like, I mean, you have the term ecosystem, right? You have the term habitat. So there's like all these different systems, and systems thinking is more natural to them. Like you have the fish behavior, the fish flocking, for example, and all of these are systems understanding. So this brings us to the role of accumulation in climate change. And when we think about it, I showed you there was already some system view on climate change, right? But something that's actually very important in climate change, and John Sturman, who is from MIT, tested this with his students, and he saw that many people aren't really prone to systems thinking and or even system dynamics and understanding what it means that there is the effect of accumulation. So with climate change, what happens is that in the atmosphere, you have a certain amount of CO2 in the atmosphere, and you have a certain absorption capacity in the atmosphere, right? And through emissions, you add on to this CO2 emissions in the atmosphere, and through removals or absorption, you remove again CO2 from the atmosphere. So this is very simple and basic how the CO2 behaves in the atmosphere. Also because it's a stock and it's a bathtub, this can overflow. It's nothing that's endless. The capacity of absorption isn't endless. And that being said, is just in words again, CO2 emissions enter the atmosphere through sources, which are inflows. And what are sources of CO2 emissions? Anyone? Yeah? Yeah? Cars, yes. But what would, like, the car itself doesn't really go into the atmosphere. It would be the fuels that, driving cars and fossil fuels, yes. Yeah? Yeah, so yeah, thanks. So for example, with the cars, actually it's fossil fuels, right? But then fossil fuels actually for a very long time were storage of CO2. It's just because we use them that we turn them into a source. Trees can either be absorbing or emitting, depending whether we burn the trees, then it becomes a source, or whether we grow the tree, then it becomes a sink of CO2. So sinks absorb CO2, which removes CO2 from the atmosphere, meaning it outflows. And the net emission results from difference between inflow and outflow. However, what's in the atmosphere is not what is the net emission, right? What is in the atmosphere is basically like an inventory. You can see it also like a bank account. What is in your bank account doesn't depend on what you paid into this bank account the same day and took out of the bank account the same day, but it's basically a history of what you paid into the bank account and what you took out of the bank account. So it also shows you what the state of your bank account is, and with emissions, it shows us what the state of the emissions are. That being said, this is the example that John Sturman from MIT used, and this is just random number, very much. And if you have a pen and paper, I would ask you to draw this. So this is the inflow at every time, and that's the outflow at every time of CO2 emissions, whatever level it is. Okay, so you start with so when you start, you have 100. You start with a level of 100, and then you have an inflow at time 1 from 75 and an outflow of 50. And I would like to ask you to draw what the level of the emissions is in the atmosphere. I have pens and paper if someone needs. So your stock in the beginning is 100 here. And it doesn't have to be like super precise, it's more about an idea. I can. Actually, we do this in class at BOKU also. And this year was the first year that students mostly got it right, which is quite interesting. So maybe something changed in the way things are taught now. Okay. Do you need more time still, or can I? Okay. Any idea why I put in this exercise? It's not to test your mathematical skills for sure. Anyone, any idea? Okay, so basically if you have a line like this, that's nice. And what you see in system dynamics, it's often talked about counterintuitive behavior. What is counterintuitive about this? Or why is it that this makes climate change more complicated? Yeah. Yeah, exactly. There is a delay, right? So the peak of emissions isn't when the peak of the level in the atmosphere occurs. And that's not how we usually think. We are more used to, our brains are more used to thinking about, oh, this is where we have the highest inflow. That's why the level is probably highest, but there's a delay. And that's very important when we talk about the atmosphere and climate change. Because currently the inflow is about twice the outflow. So first of all, we are adding to the level constantly. And yeah, that was the answer. But what does this mean for net zero emissions in the atmosphere? So when we talk about net zero emissions, and we know that currently we add twice of what is outflowing and we have a delay, what does it mean when we talk about net zero emissions? Anyone? No. Okay. So what it means is that even if we have net zero emissions, it will take some time until we get back to the level, so like the CO2 emissions in the atmosphere that we want to have. Because there's this delay that's caused through the outflow being smaller than the inflow currently, and then also over time. It's not like if we stop emitting now, we will be safe, because we still have processes going on that will take time for the CO2 to be removed. And on top of this, and I'm sorry for it to get a bit gloomy now, it will get more positive later, I promise. And on top of this is that we also have feedbacks in climate change. So there are feedback loops for climate change or acting on climate change. Anyone has any idea of what a feedback loop could be in climate change? So meaning that the more climate change we have, something happens that will create even more climate change. So that, yeah? That's exactly what I have on the slide. That's really great. Thanks for this. So actually that's something, and that's a reinforcing feedback loop. There are two types of feedback loops, as we will see in the next example, but that's a reinforcing feedback loop. And the albedo effects, would you like to explain it, or?
Sure. So basically, the snow and ice that is on mountaintops has the albedo effect. So it reflects sunlight away, and the more climate change exceeds, the more the snow and ice melts, the less white we have on mountains, and the less we can reflect sunlight, and this in turn affects.
Exactly, and that's exactly what this diagram tries to say. So there's a reinforcing loop, ever increasing this, right? So we don't only have accumulation over time, but actually the process itself reinforces itself. On top of the albedo effect, you also have more evaporation. And I'm not sure who was aware that, I wasn't for a very long time, I have to admit, that water vapor, so basically just water, when it gets into the atmosphere because it's getting warmer, is also a greenhouse gas. So the more higher the temperature gets, the more evaporation you have. The more evaporation you have, the more greenhouse gases, so the higher the temperature, and so on and so forth. So that's on top of the albedo effect. Another positive feedback loop, or like positive, that's just referring to the polarity of the loop, meaning it's reinforcing and ever increasing itself. It could also be reinforcing and ever decreasing itself. So it doesn't, positive feedback or reinforcing doesn't always mean growth, but in our current system, it does often mean this. And another example would be permafrost. Anyone who has heard of permafrost in the Arctic? Yeah. So Antarctic. So that's basically mean there's a lot of CO2 stored there, and if it warms up and it melts, there will be more CO2, meaning it gets even warmer, so even more melting, and then so on and so forth. Albedo was a bit more known when I was studying, and now I have the feeling permafrost is actually a bit more known, the problem there. So this leads to non-linear growth, because it's not just every time step you have a change in temperature, right? But it's actually every time step you have a change that ever increases itself. So in the beginning, the effect doesn't look too bad, but then after a while, you get this effect that it's ever growing, and that's exponential growth. And this is something we can also often not grasp, is that human brains tend to overestimate in the short run and underestimate in the long run, especially because we can't grasp this complexity here. Yeah. Additionally to this, nonlinear behavior can also mean, like it's the case for Antarctic ice actually, that you just certainly have tipping points that you reach, and then there's a jump. Like in 2007, there was a huge ice melt, and no one could foresee this or really explain how it happened. It's just that there was a tipping point that was reached, and then there was a huge ice melt, which again then reinforces this. Talking not just about climate change, because sustainability also is about something else, and yeah, that's something I found. Energy and efficiency, and especially the rebound effect. Anyone has heard about okay, so basically, has everyone heard about energy efficiency being very important for saving our climate? Who has heard this? Who has heard we need to increase efficiency so that we will be able to decrease emissions? Yeah. Okay. Who has heard about the rebound? No, Chevans paradoxon? Yeah. Anyone? Okay. So rebound basically is what happens if you put energy efficiency measures in place, because the way our system is structured. And this is about feedback and inefficiency and rebound. So the idea is the higher your efficiency of cars, the lower your emissions. Negative link here, meaning, and this is a method called causal links or causal loop diagrams, and it's a very useful method to explaining behavior, dynamic behavior of systems over time. So I will show an animated graph, but I would also like to explain a bit how the method works. So basically you have elements and variables in your system, and you link them through causal links. And so explaining how they relate to each other. And if it's a minus, it means it's a negative relationship, but it just means that they behave in the opposite direction. So the higher the efficiency of cars, the more emissions, the less emissions you have. Also true, if there's a minus, would be the lower the efficiency of cars, the more emissions by cars you have. So it's just explaining whether it's behaving the same or opposite direction. It doesn't really tell you which way it behaves. It just tells you what the general relationship is between them. And then it depends on how your system is tipped, whether it behaves in the one or the other direction. Okay, so there was a lot of there were, as you are aware probably, there were huge problems because there were so many emissions by cars. So there was a lot of pressure that was put on policymakers to deal with these emissions, right? And I'm not sure, can we zoom in here? So we saw here, you have a lot of emissions in the car. So to reduce them, what should we do? We fix the efficiency, like we make them more efficient so that we have less emissions. And here it says pressure on car manufacturers. So that could be a policy or just people demonstrating whatever the pressure is, right? Okay, so you had a balancing feedback in your loop. So the higher the emissions by cars, the more people would go on the streets, the more policies would be made that pressure people or manufacturers into creating more efficient cars. So there's a positive link, meaning they behave the same directions. The more emissions, the more pressure, the more efficient cars. At the same time, this also means that the less emissions you have, the less pressure you get, and the less efficient car. So that's again just the same behavior. And I'd like to play this because this is also animated. And as I said, this just gives you a general idea how the system should behave, right? Now I have to decide whether in the beginning, I could say, for example, emissions were growing. And then I click here and see how they behave. So it becomes less and increases again over time, right? And that's just balancing itself out because we have this effect of positive and negative feedbacks interacting with each other. Any questions, any comments to this? No, okay. And then this leads us. So this is what happens, right? It's also not really great if you think you want to ever endlessly reduce efficiency, but at least efficiency would reduce over time and would balance at some, like emissions would reduce over time and they would balance out after a certain while. But then what happened actually is this is embedded in an economic system, right? It's not just because, are you aware that the efficiency increases, they never really were realized? So we had efficiency increases, but we never reduced our emissions really. And this is because one of the reasons, because this whole thing is embedded in an economic system. And the logic of the economic system is that the more efficient cars you have, the more affordable the cars get. And the more affordable car use is, the more you use your car. And the more you use your car, the more emissions you have. So, and then you have more pressure again, which again means you have more efficient cars, which means you can use them again more because it's more affordable. And that's a system structure, right? That's a system structure that wasn't thought about before implementing this measure. And that then was discovered later on. And what you see here is let's start with emissions also, or let's start with efficiency increases, right? So let's assume we increase efficiency. What happens is that for a while, it goes back and forth, right? But because we have this reinforcing loop here, after a while, everything else just increases crazy because you have this reinforcing behavior here. And that's something you didn't see before down here. You didn't see that it went from one extreme to another extreme. And that's because we missed to capture this feedback that also exists in our system. Is it clear? I mean, yeah, I hope this animation made sense. That's the first time I use it when I explain this, but in case it doesn't make sense, just let me know. Yeah, maybe showing again what, like, you saw that this went all the way to the boundary, right? Although I pressed decrease efficiency in the beginning. And here, just to show you the effect again, is that when I press decrease in the beginning, yeah, it also goes all the way to the boundary, it shouldn't though. Oh, no, sorry. I pressed increase efficiency in the beginning before, so when I say here increase efficiency, it never goes all the way up here. And that's a difference in how our system behaves, right? And the outcome we get from our system, depending on whether I set my system boundaries here or I set my system boundaries broader and I look at the system it's embedded in. Yes?
And in the second case, everything just slightly goes to the maximum and then back to the minimum.
Yeah, I mean, this is just, that's not how real the models work. Yeah, so it does go back and forth, but it depends on, of course, how exactly you parameterize these values. But going back to the presentation, unless you want to see the colorful bubbles again, I think we have seen the bubbles. Yeah, so what you get is you have one balancing behavior, and that's what you actually intend to get if you want to balance your emissions. And then you get a reinforcing behavior that you didn't account for before. And this is it's an archetype actually. It's called fixes that fail. So if you see a graph that behaves like this, you can assume it's a behavior like a system structure like the one I just showed beneath it. And what you get is that's your problem. So your problem behaves like this. And they just assume that it's actually increasing still. So it doesn't really level off at some point. And it drops, but then it comes back up again. And it drops and it comes back up again. Plus, on top of this, you have an unintended consequence. And in our case, would be the increased car use, meaning you have even more cars on the street. And then if you embed it in an even broader system, you could have more cars on the street, meaning you have congestions, meaning you have delays again, and all of this, right? So this was just one example of how setting different system boundaries and how understanding the structure of the system can also understand you how a system behaves over time, not just for that one moment. And especially when we deal with social systems and economic systems, that's often what we miss. We think about technological solutions, but we miss that there is a structure where we put this technological solution in, and we don't understand how the structure actually will take on this technological solution. Yeah. So this was a demonstration of how feedback leads to non-linearities and delays in the system also. That being said, so these were two examples, and I could go on with examples, but I mean, I'm not sure. This was just to demonstrate how it works. Sorry. Yeah, so basically rebound means that efficiency gains aren't realized because of either short-term, like direct economics effects, so I can drive more, or I just invest my money in something else. So I might not need as much money to drive my car anymore, so I fly somewhere. And then it's not just that the efficiency gains weren't realized, I actually emit even more because I have the, I just use something that's more resource intensive and more emission intensive in the long run. So that's the rebound effect and seventh paradoxon. And I think that's a very good example of how missing to understand system structure can lead to wrong solutions or misleading solutions. Something you could do is that you add in that you don't let your products get cheaper if they get more efficient. Also complicated because then there's a question of fairness and all of this, but these are like, that would be something you would have understood if you had looked at it. Like, this is something we understand when we look at it from the systems perspective. That being said, it's not just that within each of these SDGs, right, there are systems. There's relationships between all of the SDGs that link the SDGs and that influence each other. There are feedbacks between them, creating feedback loops. So we really shouldn't look at the SDGs like in this table form, I would say, but we should look at the SDGs as a net and as an interactive entities. And this means that change in hunger, changing something about a target we have here, can also lead to a target that we have here in affordable energy change. And all of this, and then you you have feedback. So reaching all of the SDGs next to each other would be summing them up, right? But that's not what's happening. And the positive news about this is that you can have synergies. You can harvest synergies because you might create positive feedback loops that reinforce each other in a normative way, in a good way, in a good sense. At the same time, the bad news is you have trade-offs that you can get because they are linked to each other. And if you look at the system and understand how the system structure works and how these entities are linked, then I think you can minimize trade-offs and you can actually increase synergies. But that's if you understand the system structure. Yes, so this was what the SDGs were put out as in 2016. And it's astonishing that they weren't portrayed in a more linking manner, right? But in 2017, the United Nations, the World Health Organization, and the OECD all declared that system thinking was a key leadership skill and necessary to deal with the fundamental interconnectedness of complex local to global economic, social, and environmental issues. So that's when they recognized, oh, there's an interlinkage, and we need to understand this to actually to address the challenges we face today. Beyond of this, why am I talking about systems thinking and systems change, and why is this so important? And why is it so important, I think, is because we need systems change is one of the most mentioned phrases or quotes when it comes to climate change, right? You've probably all heard about not climate change, but systems change. But what does systems change really mean? And system change means not just changing our reaction to wildfires. It also doesn't only mean understanding what will happen and then try to prevent it. What it means is changing the design, how our system is structured, understanding the levers and changing it and transform out the goals and the values out of which the system arises. More detailed, this is what Donella Meadows came up with, and astonishingly, I mean, this graph is from 2017, but this was published in 1999, right? So has been a while, and I think it's still very relevant today. Looks a bit similar than like the iceberg, right? So where can you intervene in a system? A leverage point is a place where you can intervene in a system. So that's what a policy can address. A leverage point isn't a policy per se. A policy can address a parameter, such as, for example, taxes or efficiency increases. A policy can address the structure of information flows, which would be like, it can also, a policy can also address the length of delays. So if you, for example, or not a policy, but you can change the length of delays, for example, adding another resource to your already existing resource pool means you'd have more stocks available, which means you'd run out of it later of that resource, which means you would have a delay there in using it up. A policy can influence, for example, structure of information flow. So, for example, who gets access to measures of what values? What do we measure even, right? What are the values we measure? And what we measure is then also what we base our decision on. So this means that we change the structure by providing new information, maybe giving someone else access to this, and then changing the system of structure. And this then here is a bit more tricky. And as you can see, the further down we go, the deeper they get, meaning also they get more tricky to implement and more complex to understand. And one would be the goals of the system. So if our goal is to grow GDP indefinitely, there's a certain behavior and structure we create within our system. But if our goal is to save the environment, we need a very different structure of the system, and we will act differently. Then the mindset out of which the system arises, so our values, and last but not least, the power to transcend paradigms. And that's getting a bit, actually it says spiritual on here, so when you read it, it sounds a bit like it, but basically what it means, it's making it resilient, creating resilience in our own worldviews and the resilience in the system, so that when the outside factors of the system change, the system can adapt, and we're not so locked in structures that have so huge delays built in there that we cannot change. Yeah. So this is on the leverage points and how to change system. Most policies, and I've done a review on this in 2017, I think. 18 was part of my PhD actually, that we looked at energy policies. And a lot of policies would focus on parameters because that's the easiest to tackle. It's not very much, you don't have to understand a lot of complexity of the system to tackle a parameter. But also it's not as effective at changing the design of your system. installing renewable capacity would be the length of delays relative to the rate of system change. The structure of information flows would be, for example, providing technology knowledge to low-income countries so that they can leapfrog, which is very important. And the rules, and then the goal of the system, for example, would be changing from ever-growing to a sufficiency level. So instead of having efficiency, making the goal of the system sufficiency would change the system structure and would change the system. So in order to know how to tackle the deeper leverage points, it would help you to understand the system structure. Yeah, so what systems do we look to transform? And here I'm going to go back again, and that's our society. I think I took this as a transport system, an urban system, our food system, our agricultural system, our production system, and our industry systems that we have, our energy system, very important, also because that's the field I work in. I mean, also agriculture is very important. Every one of these systems is very important. And I think if we really want to change those systems, we need to understand the system structure, especially if we want to really change them deeply and not just make small changes. But if we really want to transform them, we need to understand where accumulations, for example, power plants, create huge path dependency and lock-in in your system because they have a long lifetime, and there's no point in building up a power plant that you scrap after 5 years again. Where are feedbacks in our system, and where are the resulting delays and non-linearities, and where can we use these feedbacks, delays, and non-linearities to actually change the system? Is this news to us? And I will, looking at the time, just quickly run through this. No, it's not news. You have probably heard about the limits of growth. Yes. And this was published in 1972, so 50 years old, older than all of us who sit here. And what they did is, it was the first model that connected pollution, capital investment, so the economics kind of, to population, natural resources, no renewables, just fossil fuels, and agriculture. And they saw that there was ever increasing pollution. Back then it wasn't climate change, but there were other issues like nitrogen and these kind of things, DDT. Then they saw that this was around the time of peak, like where the oil crisis happened, right? So resources back then had a different meaning still also. And they saw that there was a huge economic growth going on, but population and health weren't really improving. So that's why they came up with this study and built a model that had these 5 sectors that interacted. And although it's so old, in 2000, the most, Matthew Simmons said, the most amazing aspect is how right they were in many of the basic trends extrapolations. And that's not saying that they got the numbers completely right, but, and also actually, we can still see that they're almost right still nowadays. And what they got right were the general patterns over time. It wasn't that they got exactly right how many people will live on the earth, or how much food we will have and consume, and how much pollution we would have, but they got almost right how those variables relate to each other. And the BOKU scenario, the business as usual scenario, basically just said that because we will hit our, because there will be less food available, less renewable, less resources available, we will have slower industrial growth, which then will also, and both will also lead to a population decline. And this comes with a delay in the system. Double the resource was also a scenario they had, and they didn't really model technology in there, but double the resource could also be understood as technological improvements, right? What led double the resources to was that the pollution absorption mechanisms didn't manage to capture all the pollution that was created by using double the resource. Also something we observe today, right? And even though we had double the resources were depleted in the end almost anyways. So yeah, this is resources, and it also goes very low, although we had double the resource in the beginning. There were scenarios where this didn't happen. And what was significant about these scenarios is that basically they tested new policies leading to new system structures. So double the resource didn't really change much in the outcomes, right? There was still a collapse, but changing the system structure would change how the system behaves over time. And I just, to be honest, I don't know exactly what were the assumptions. Like, there were several new policy scenarios, and I can't tell you exactly which one this was. But what I wanted to show you is that here you don't have these collapsing curves all over the place. And that's because there was a new system structure. So what do we need to do? I think we need to think outside of the box. And that's something I picked up from an event I was at where Wolfgang Peckney was, the person who does the footprint network, or he does footprinting. And we had a very doomsday discussion, as usual, when you talk about sustainability and climate change and how we will never manage to reach these targets that we set ourselves. And then he said he has experienced with he got everyone to one footprint, to 1 hectare per person of material, or one planet, whatever you want to call it. And how this usually happens is that he gets the people to think outside of the box. So thinking about solutions that aren't in our current system, that we can't even think about now. So thinking also about new structures of the system that would enable new solutions that aren't possible now. We also have to act now, and that's what they already said in 1972. So I think it's really now that we need to act. And I would argue that you also have to think about structures, not just numbers. So think about if you change your mobility, pattern of mobility from flying to sailboats, what would that mean? What type of boat would you use? How does this relate to the system we have now? If you change your food system, the food you eat, what's the structure you embed your new solution in? And maybe what other structural changes are needed rather than just replacing one with the other. Yeah, because we might live in a future like this, or we might live in a future like that, or like this. And that's Simona Koch, and I really invite you to look at her blog. She has really cool pictures there. Also portraying how a future could look like, a sustainable one, how it might look just different, right? And no matter which future you choose, if you really want to understand whether the future can be sustainable or not in terms of social system, but also environmental system, I think what you need to look at is what system do you embed your solutions in, and how is this system structured? Where does this system get its energy from? Will there be a fair distribution of those flying cars around and these things, right? Because just having the technology of building high buildings and flying cars doesn't really get you anywhere. You need to understand what is the structure, how will people use this, to understand how sustainable your solution is. And I invite you to think about outside of the box of all of these futures, and then try to understand what the structure is in these futures to really grasp it. And also understanding what the structure of the future is, you understand what changes from the current structure need to be done. Yes, thank you. That was it.
Thank you very much. Yes, just a compliment.
Yeah, any questions, of course.